Um, Thank you for the opportunity to share my work with the community. Okay. Um, Today, we talk about recent project regarding black holes in fourth dimension, considering Einstein power Maxwell nonlinear electrodynamics. Um, and this work was made with some collaborators from Chile and Spain and Ecuador and other countries. Okay, so the main idea uh, of this talk is basically summarize the main ingredients uh, used to compute solution in scale-dependent gravity. Okay, so I only want to discuss the key points. Okay, well, this talk basically have a very short introduction, and after that we will move to the problem to be solved. We first start with the classical problem, and then we will move to the quantum version to the problems. So, scale-dependent gravity, roughly speaking, try to add quantum features to classical solutions. This formalism works well, for instance, in black hole physics, in relativistic stars, and recently have been applied to cosmological models. Okay, so the idea is first uh, be first is try to introduce the classical model, and after that apply the formalism and compute the new solutions and compare the scale-dependent solution with the classical counterpart. Okay, that is the idea. And at the end of the talk, we summarize the main points in a take-home message. Okay? Well, regarding the introduction, as I previously said, we want to incorporate quantum gravity or quantum features to classical solutions. And we know that in order to understand quantum gravity, we can, for instance, we can apply different approach to make progress, to get insights about quantum gravity. One of them could be asymptotic safety, or another related approach in which the parameter which describes the theory acquire a scale dependence. Okay, we have several scenarios in which gravity can be tried to incorporate to quantum mechanics, but I will only focus on the asymptotic safe idea where the theory evolved to a version theory where the coupling constant evolved to functions. Okay, so this scale-dependent gravity, which is similar to asymptotic safety in this fundamental idea, basically adopt this assumption that the couplings which appears evolve. This is the underlying idea here. Okay, so we want to first consider an example, which is the motivation of this talk, which is the nonlinear electrodynamic, in particular the Einstein power Maxwell solution in four-dimensional space-time. The classical solution was first found by Hassiani and Martinez more than 10 years ago. And well, basically they discuss four and higher dimensional solutions. This talk is only focused on four-dimensional black hole solutions, okay? So the classical solution have this action, the Einstein-Hiller plus the nonlinear term. And we can, of course, derive, taking the corresponding variation of the action, we can obtain the effective Einstein equations, where the mu encode the nonlinear electrodynamic part, okay? So when we compute, irrespectively of the kind of electrodynamics, we have also write this in this form with an appropriate answer for the electric field. You can also include magnetic field, but this is another discussion. Taking this particular form of the electromagnetic tensor and this answer, the answer of the line element, we can compute, for instance, we can compute or obtain this equation, the equation for the electric field, that can also be solved exactly always. In the classical case, can obtain the exact solution, and in this case, we also can obtain the exact solution too, okay? And basically, we need to find the lapse function and the electric field. We are using the Schwarzschild answer as always, okay? Good. This is the above mentioned solution, the Hasiani and Martinez solution, where they found this Reiner-Nostrum-like solution, where the alpha is connected with beta in this way. And beta is the index of the nonlinear electrodynamics. Just see this part. We can see the definition of the nonlinear electrodynamics, and basically beta is the exponent. Okay. Okay. Well, we also recompute this because we need to compare the classical with the scale-dependent solution. That is basically the classical solution, avoiding details. And of course, as say in the paper of Martinez, we have a relationship between the parameters given by this last equation, okay, adapted for the four-dimensional case. And for our solution, we will set the constant according to this choice of parameters, where A, B, C, and D correspond or are connected with the classical parameters according to these identities. And well, this will be used later. Okay? The black hole horizon is also obtained with the classical condition, demanding that the lapse function is equal to 0. And in general, the case is not possible to obtain the analytical solution. So we only can write the lapse function in terms of the critical points, which are the 0 of the function, but we cannot obtain directly what is the horizon. Okay, this is this condition can be used to identify the critical points easily, but in the scale-dependent version, that is not possible to obtain because the functions involved are quite complicated. Okay. Well, the thermodynamics is computed as always. I am avoiding the details how we can find these parameters, but we can compute the temperature, the entropy, and the specific heat according to these relations. And still, in the classical case, we cannot obtain a closed form to the temperature, although you can you can obtain the derivative of the last function, but we prefer show the formal expression. Okay. Now let me move to the action with running couplings. What that means? Well, we take certain action and we promote the classical coupling to the scale-dependent couplings. So we have two coupling in this case: the Newton coupling, which is kappa sub k, and the electromagnetic coupling, which is A sub k. We again derive the corresponding effective Einstein field equations, and in this case, we'll obtain an effective version of the energy momentum tensor, which take into account the running of the Newton coupling by this term, okay, this delta T mu term, which is typical in scalar tensor theories of gravity or in FR theories. And we have an additional equation to be computed. which is the equation obtained varying the action with respect to the auxiliary field K. But in general, such equation is quite complicated. Basically, it's highly nonlinear. The idea is try to circumvent this equation, avoiding the loss of information. So at this point, we try to apply some additional condition to replace the original equation. So in this case, we recognize that the null energy condition can provide us the information to proceed with the computation. And in this case, we replace this last equation with the implementation of the null energy condition. And also we accept that, or we recognize that all the functions involved depend on certain scale K, but taking into account the symmetry of the problem, we know that this scale at the end of the day depend on the radial coordinate because we are considering a spherical symmetry. And finally, all the parameters acquire a radial dependence. Okay, and with this in mind, we can rewrite the equations and also compute the solutions. Okay, and avoiding the details, but we can summarize the main idea. Okay, firstly, we have a given the null energy condition provides a second order differential equation which can be also solved in the saturated case. That means that as you know, the null energy condition is inequality. We in this case consider the saturated case, which means consider the inequality equal to 0, and we can solve this and obtain an exact form of the Newton's coupling. And after that, we can replace the solution to first obtain the electric field, which is also obtained directly by the direct integration. And after that, we compute the lapse function and the electromagnetic coupling according to these solutions. Okay. This is when we have a few special functions. We have a beta function here, and these are supplementary functions which are defined in the next slide. We have these auxiliary functions, nothing special, okay? But and this is the incomplete beta function, which is defined in this form, okay? So this scale-dependent solution should be, of course, should be recovered, or should recover the classical solution when epsilon, which is the parameter that encode the quantum features, is taken to be 0. So when we take the appropriate limit, we recover the Hayani and Martinez solution. Yes, and we need to, or we also want to compute the corresponding thermodynamics. First, we compute the horizon, or we try to compute the horizon, but in this case, that is not possible because the complexity of the lapse function, as you can see, we have a non-trivial function, and that makes it impossible to compute the solution. Okay. Well, we just to exemplify how this works, we take the concrete value alpha equal to 2 and expand around epsilon close to 0. And we obtain that the scale-dependent horizon, as can be observed, is shower than the classical counterpart. Okay.
3 minutes.
Sorry.
3 minutes.
Thank you.
Yeah.
So you can observe that. Well, let me first explain the color code. The black line means the classical solution, and blue, green, and orange corresponds to the scale-dependent solution. And epsilon increase from blue to orange. So when you increase the epsilon parameter, the black hole horizon is smaller. So which is consistent with this expression, okay, for the case alpha equal to 2, okay. Yeah, that information can be confirmed with this figure 2, okay? The same code when black is the classical solution and the color code or the other lines in color correspond to the black hole horizon, okay? For alpha equals to 2. Well, now the thermodynamics, well, as the horizon cannot be obtained analytically, we also can compute the temperature taking an expansion around epsilon close to 0 for alpha equal to 2. Okay, so we observe that the temperature increase with the inclusion of scale-dependent couplings, and the entropy and the heat capacity also are modified by this additional term, epsilon r sub h, which is absent in the classical solution. Okay, let me show a numerical treatment of this. We observe the temperature, of course. Black is the classical solution, and color lines correspond to the scale-dependent version. We observe that the temperature increase when epsilon increase. Okay, the entropy decrease when the epsilon increase. Okay, within the details, these features cannot be easily inferred from the solution because the solution is given in terms of the implicit horizon. Okay, but we have confirmed this in different cases. To summarize the idea, okay, this formalism scale dependent introducing an additional contribution to the energy momentum tensor, which is of course standard in scalar tensor theories of gravity. Just in this case, we reinterpret the term by the running of the Newton coupling. In this approach, the integration constant play a crucial role because when we recognize that the Newton coupling obtained back under this formalism have two free constants, and we identify one of them of the parameter which encode the scale-dependent formalism, we recognize the importance or the impact of the integration constant. Okay. We also observe that we have two clear range which depend on the impact of epsilon on G sub r. Okay, when the impact of the scale dependence is important, you have a strong deviation respect to the classical solution. And on the other hand, when epsilon is close to 0, we will of course recover the classical solution. Okay? We have a deviation, at least in this in our computation, to the area law, to area times radio law, which appears in the entropy. Okay. It is not possible to compute exactly the entropy and the specific head because we don't have the specific form of the horizon. And finally, the specific heat indicates that the black hole is unstable, similar to the classical counterpart. Okay. And we have an extra slide which can circumvent this by the moment. Okay? And that's all.
Okay. Thank you, Michael. Questions. I see Carlos Contreras has a question.
Yeah. Okay, thank you for the opportunity to ask. I would like to ask you about this idea from the asymptotic safety you're commenting in this talk. Usually when you study this gravity with extra term from mass term, in this case, you have the flow equation for the running coupling the momentum space. And then you move to the coordinate space to this correlation with Q and R. Do you have some comment about this flow equation? Because that is another option to obtain similar result, I can imagine.
Yes, it's an alternative form because you have to, let me try to explain this. You have you can compute the flow when you have the beta functions, right?
Mm-hmm.
But in this case, we avoid to obtain the exact beta function, basically because we don't we try to take advantage of the idea that the couplings evolve with certain dependence, and we incorporate certain supplementary equation to complete the set and solve the solution. But we of course can try to compute using the standard route, which means compute the corresponding beta functions and compute the flow. In this kind of works, up to now in black holes, we have not any paper with this inclusion, but recently, previous year, we published one paper where we compute the solution using scale-dependent gravity and compare this with the solution obtained by asymptotic safety gravity in cosmology. Okay, so this is the one of I think that this is the unique paper where we compare the two approaches up to now. Okay.
Okay.
Okay. There's another question here by Cristobal Corral. It says, is the first law of thermodynamics satisfied by this black hole solution?
Yes, when you, but it's a little bit delicate this part, because depending on the value of epsilon, we can violate certain assumptions. For instance, depending of this value, of the epsilon value, you can, for instance, have an entropy potentially negative, which of course is a problem. So in general, the thermodynamic is susceptible to this to the scale-dependent gravity, in the sense that we need to select properly the epsilon parameter, because the sign is important in general when you compute the thermodynamics parameter here. Okay? And indeed, recently, 1 month ago, collaborator published a paper regarding the first thermodynamic law in scale-dependent gravity. Maybe something more more in depth regarding these quantities, but the study is more or less the same. Okay.
Mauro, you had your raised hand.
I don't know if we have time.
Well, we don't have time, but I mean, if it's short,
okay,
try.
so I will pose the question, Angela, and if not, then you reply on the chat box. So usually in theories with boundaries, there is a subtlety regarding the continuity of the energy momentum tensor across the boundary, either the tensor or its derivative. So my question is, if these additional terms that appear in your model, do they have something to say about this continuity of the tensor or its derivative?
I don't know.
I mean the boundary of the horizon.
Yeah, because no, I need to think about that, because this additional term is usually obtained in the same way that you obtain a term in effort gravity, which means that you take the corresponding variation and you now identify an extra term, you integrate by parts, and this new term is in this case identified as this delta T mu, basically taking the corresponding variation. Is it the same procedure using in FR gravity or FT gravity, things and theories like that? But I don't know if this is directly related with the energy momentum tensor at this moment. Let me think. I can mail you after that. Okay.
Okay. Thank you.
Okay. So we thank Angel for the talk.